Okay, in this video we're going to look at design assurance as a way of achieving system safety. First we'll review the learning outcomes, and then we'll look at advisory circulars after 25.13.09.1a to show compliance of systems that are even more complicated. And these are going to involve authorizing the use of SAE, Society of Automotive Engineers, ARP, Aerospace Recommended Practice 4754 and 4761 to show compliance. And then RTCA DO-178C, not B, for airborne software, 254 for airborne electronic hardware, and 297 for integrated modular avionics. We'll talk about the details of some of what those are. When you get done with this module, you should be able to state the essence of 14 CFR 25.13.01 and 13.09, explain how advisory circular 25.13.09 defines extremely unlikely, unlikely, etc., and explain how SAE ARP 4754, 4761, and RTCA DO-178C and 274 figure into aircraft certification. So 25.13.01, 14 CFR 25.13.01, the regulations on function and installation says basically a system's got to do what it says it's going to do. And then 25.13.09, Part B says that the requirement there should be an inverse relationship between likelihood and severity. That system monitoring, and you should have system monitoring, you should give failure warnings, and you should give the flight crew ability to respond to failures, and you can demonstrate compliance by analysis. So previously we talked about how do you demonstrate compliance with 13.09. And we talked about advisory circular 25.13.09.1a, which does specifically that, gives some guidance on how to show compliance with 14 CFR 25.13.09. Talks about fail-safe design, minor, major, and catastrophic consequences, what those are, qualitative and quantitative probabilities associated with those consequence levels, and the kinds of analyses that you can do, which was functional hazard analysis, preliminary system safety analysis, etc. Since 25.13.09.1a, which was published in the 80s, there's been additional advisory circulars that talk about how to deal with increasingly complex software and hardware systems that implement avionics, including what's called integrated modular avionics, which is where you have networked avionics hardware, you've got a flight data box, you've got a air data box, you've got your inertial navigation, inertial measurement units, and all these things can talk to a common computing core, either over a data bus or a network, or if they're all internal to, if they're all physically attached to the same microprocessor using the computer's data bus. So the first one of these we want to talk about is Advisory Circular 2174, which is the development of civil aircraft and systems. And this is what authorizes the use of SAE Aerospace Recommended Practice 4754, which is called Guidelines for Development of Civil Aircraft and Systems, for what's called design assurance. And we'll talk about design assurance in a minute. But it also references what's called, which is another SAE document, ARP 4761, Guidelines for Conducting the Safety Assessment Processes on Civil Airborne Systems and Equipment. So design assurance is just anal retentive software and hardware design. Discovering, preventing, and correcting errors earlier in the design engineering lifecycle when these problems are less expensive and possible to correct. That's from the Alan Turing Institute. So it's a very structured, watching over, constantly picking at kind of development process where everything is documented, everything is recorded, records are kept, and a reduced amount of change only happens under certain conditions, and different levels of change are allowed for different levels of safety. But 4761, the second one of those mentioned, the Guidelines for Conducting the Safety Assessment, tells, I mean, we've already talked about some of these processes like functional hazard analysis. Again, the functional hazard analysis, we go over the aircraft and its systems and talk about potential failures that are associated with each one and determine whether the failure would be a catastrophic, severe, major, or a minor consequence. The preliminary system safety assessment is where you go through and you establish the safety and for the system and the safety requirements for each item in the system, and your preliminary design gives an indication that we should be able to meet the requirements. So then some other things, as you continue forward, you actually do the system safety assessment. The system safety assessment is when you collect and you demonstrate, you verify that the system meets the established safety requirements. And these can be done through fault tree analysis. We talked about that previously. There's a failure modes and effects analysis. So if this fails in this way, it's going to have this impact. If it fails in this other way, it's going to have a different impact. And you can capture all those in what's called a failure modes and effects summary. And then there's a common cause analysis. And this includes what's called a zonal safety analysis, particular risk analysis, and common mode analysis. And so the common cause analysis establishes and validates the physical and functional separation and isolation requirements are there, and it verifies that those requirements have been met. So you've got these different tools for demonstrating safety of individual aspects, modules, components, elements. So to do design assurance with 4754, you use a functional hazard analysis to identify the hazards. You chunk the system into a hardware and software and different modules there, and you have safety plans, and you have an architecture that should allow you to achieve assurance level. That could include redundancy, dissimilar systems, similar parallel systems, and the like. We'll talk about some other ways of achieving these. You can designate design assurance level appropriate for failure conditions. And so again, we've talked about these different failure conditions: catastrophic, severe, major, or hazardous, major, minor, and the like. And so under ARP 4754, these are given letters, just so you don't have to say catastrophic hazard. You have level A, B, C, D, E for each of these. And then you design to achieve level A assurance, level B assurance, etc. So once you get your design nearer, that's when you perform the system safety analysis and the common cause analysis as more of a demonstration that your design works, whereas the FHA and the PSSA have to do with the developing the system and prior to the design when you're chunking things up for your design. So some of the ways to achieve specified design assurance levels, these aren't particular either A, B, C, D, or E. These are just some different processes that give you different value. Partition design, so you can isolate faults. So you can then now talk about the failure condition for each portion and design each portion to an appropriate design assurance level. And then when you put all these together, you have to achieve the overall design assurance level. So it may be that to achieve a design assurance level A, you can have subsystems that are design assurance level B, but when they're combined, you get design assurance level A because of redundancy or hot swaps or something. So again, you can have the similar independent designs and develop your design assurance level for each. So each channel can be lower that way, and these can be done with primary with backup. You can have an active monitor design where it's active monitor means you've got two things running in parallel, monitoring each other to make sure they're both working, or two or three even, and if one fails, the other two voted off the island kind of thinking. You can have parallel backup design, so you just swap in where you were last to get things going again and the like. So again, that's at the system level, and that's using ARP 4754. Which references 4761. On the software side, Advisory Circular 2115, which is called Airborne Software Development Assurance using EuroCAI ED12 and RTCA DO-178, gives you a way to show compliance using this RTCA DO-178C. The EuroCAI document's the same thing. The committees that develop these met jointly. In fact, Embry-Riddle hosted these. My colleague, Dr. Korneski, who's retired, was one of this part of this working group, which the RTCA calls Special Committees, SC. So DO-178C is called Software Considerations in Airborne Systems and Equipment Certification. And it's got a bunch of other documents that were developed around the same time as when they went from B to C, actually. When the revision of 178 went from B to C, they added these other documents that give ways to qualify and what tools did you use. Did you use tools, automatic code generating tools and the like? So those have to be qualified, and if you use automatic code generating tools, then your design, if you use a certain tool that's been qualified, then your design is further along towards being certified. 331 and 332 refer to model-based development and verification and object-oriented text. So, I mean, prior to 332, object-oriented was not even allowed in flight systems. And even then, it has to be deterministic. So if languages like C++ are okay, but Java, which has a garbage collection system that's performed randomly and stochastically, is not okay. And then formal methods, 333 references formal methods. This is a way of demonstrating that your system should be compliant, and that uses a computer. I mean, you can use languages like Z, which have formal methods built into them, or you can do abstract analysis after that. The other document reference here, the DO-278, which is referenced in 331 and 332 here, software integrity assurance considerations for communication, navigation, surveillance, and air traffic management systems. This is software on ground-based systems, and the FAA has different guidance for airborne systems and ground-based systems. And I think that the special committees working on 178C were really hopeful that they could sell the FAA on a single set of software considerations, regardless of whether the system was airborne or ground-based, but that didn't happen. On the hardware side, Advisory Circular 2152, which is called Design Assurance Guidelines for Airborne Electronic Hardware, says you can use RTCA Document 254, Design Assurance Guidelines for Airborne Electronic Hardware, to demonstrate compliance for what's called complex electronic hardware. So as the text in the document says, it applies to the manufacturers and installers of products and appliances incorporating complex custom micro-coded components. And these include ASICs, application-specific integrated circuits, PLDs, programmable logic devices, and FPGAs, field programmable gate arrays. These are all kind of, I mean, FPGAs are reprogrammable logic, so to speak, and ASICs are custom chips designed for a particular application. It's not required for commercial off-the-shelf microprocessors, and as it says here, there are alternative methods or processes to ensure that COTS microprocessors perform their intended functions and meet ordinance requirements. But there's really, I mean, it's presumed that the manufacturers are building products that work. So both software and complex electronic hardware design are done in a lot of the same ways, and this may be unintuitive, but they're going to require the same kind of activities, because so much of complex electronic hardware design really is a programming language built around, it uses what's called hardware description languages. VHDL is one, Verilog is another, and so these both the software development and the hardware development have lifecycle constraints, and they use strict configuration management for correct design. So because you can't test every output. There's just, I mean, you know, once you get beyond so many if statements, once you get beyond so many logic gates, you're into the number of possible outputs, you know, corresponding to the number of particles in the universe and things like that. It just gets fast really, really quickly. So the base, you can't test every state deterministically. And so the approach is, do we have the right high-level requirements? Did we get the right low-level requirements from the right high-level requirements? Did the low-level requirements give us the right designs? Did the right designs give us the right implementations? And can we demonstrate, if we can't test every output, can we show that there are no outcomes that are unreachable, and there are no states that are unreachable? So again, you can't have branching in a program into a chunk of memory that's not used. That's what we're talking about, unreachable states, where random things would happen. You can't have, you can't reference part of the chip that in an FPGA implementation. You can't use a gate on another part of the chip that's not that's not part of your system. So you have to make sure that you only talk to the parts of the system. The code only talks to other parts of the code that matter. The hardware only talks to parts of the hardware that matter. That's what we mean that all cases are covered. So you have to do documentation of the lifecycle processes and the data that generates, and you have to have independent verification and validation, actually, and process quality control, testing, quality assurance, appropriate to the design assurance level. And so we mentioned you have to maintain change control and configuration control. So there can be two levels for each one of these. Level one, where all configuration management activities have to be done, meaning you have basically a static document that you can only change under the most restrictive of circumstances. And then change level two, which in software code change two, hardware change two for hardware, less restrictive. It's going to change. And here's some of how these show up in the documents. This is from DO-254. It's in section 10 here, and it's talking about hardware aspects of certification. So you have to have a plan for your hardware aspect of certification. And this, regardless of the design assurance level A, B, C, or D shown over here, this is a change control 1 situation. The hardware plan can only change in a most restrictive sense. You have to have a paper trail here saying who approved the hardware change, who approved the change in the hardware aspect of certification plan. But the design plan for the hardware is presumed it is going to change, and the validation is going to change. So you can see here that the hardware design plan, the hardware validation plan, the hardware verification plan, the configuration management plan, you can see how some of these things change. For design plan, validation plan, and verification plan, these are all level 2 on the change control, meaning you expect that this is going to change as you percolate through the process of doing your design. Whereas your hardware configuration management plan, if it's a level A and level B, that has to have more restrictive change than level C and level D. So again, there's going to be these different levels of what's allowed to change, who can change it, what kind of authority you have to change it based on where you are in the system. Here's an example from a DO-178C. This actually may be from B when I think about it here. So if we look here at item 5 under the software planning process, software development standards are defined. That's the objective here. It's required, it should be satisfied, it's an open circle there, by each of levels A, B, and C, but you don't have to have that for level D. And then where you do have to have it, the software requirement standards have to be under change control 1 for level A and B, but they can be under more or less restrictive for level C, the design standards similarly, and the code standards similarly. So again, and these tables go on for pages and pages and pages, depending on what aspects. So again, there's many aspects. It's a very restrictive, mandated, jump through these hoops, do it this way kind of process. It's onerous. I've mentioned that the certification process so that's what I'm talking about here for the certification process. Going through these hoops to demonstrate design assurance is more expensive than the actual code development itself. So for each of these, and I was mentioning how extensive this is, for a DO-178C and DO-254, you have tables for planning process, development process, requirements process, design process, coding and integration process. You have documents and tables for the testing of the outputs of the integration process, the V&V, the verification of the verification process results, and so on. Configuration management process, quality assurance process, and the like. So design assurance, whether it's referenced in ARP 4754 or whether it's referenced in DO-178C or DO-254, is a constrained process for demonstrating that your system should work. Lastly, I want to talk about Advisory Circular 2170, which is called Integrated Modular Avionics Development, Verification, Integration, and Approval using RTCA DO-297 and Technical Standing Order C-153. So IMA is connected hardware with shared computing resources. So again, we've talked about things like the air data unit, and we've talked about things like an inertial measurement unit, and we've talked about things activators. So you can have hydraulic activators in a transport category aircraft and things like the actuators. And these can all be networked and connected either via a data bus if they're in distributed parts of the aircraft. You may have multiple computing resources in a rack in the aircraft. and you may have multiple modules running on a single microprocessor talking to each other just through the main bus internal to the microprocessor. So you're talking about shared computing resources, and it's a sort of modular software talking to different avionic units. So you could have one microcontroller that's talking to, on a general aviation aircraft, you could have one microcontroller that's talking to all the different avionics units, and then running this on a time shared standard way we do computing, where you swap processes in and out for each of these things. You have to demonstrate you have enough resources for each one of the processes you're running. And that's what DO-297, Integrated Modular Avionics Development Guidance and Certification Considerations, is about. TSO C153 tells the manufacturers of the hardware units what kind of specifications they have to have in order to interact with software running on shared computing resources under DO-297. We're not, I mean, that's, I just wanted to mention that there. It's a part of what's going on in the avionics world these days. This is where ARINC 664, the full duplex avionics, full AFDX, avionics full duplex Ethernet comes into play, and the like, to coordinate these integrated modular avionics units. So we talked about Advisory Circular 2174, which lets you use ARP 4754, and 4754 references ARP 4761 for how to do the safety assessments. 4754 brings up the idea of design assurance and the different design assurance levels. And then again, in terms of catastrophic, major, severe, major, minor, etc., and giving those A, B, C, D, E names. And then those are used in DO-178C currently, and DO-254 for airborne software and airborne electronic hardware. And both of these involve, specifying the lifecycle processes, the degree of change control management, demonstrating coverage that all possible states are reached and impossible states aren't reached, and having independent validation and verification for both the software and hardware. And then AC 2170 talks about using DO-297 for integrated modular avionics. But 2170 is just sort of thrown in there extra. It's a freebie. It's not in the assessment or the learning outcomes. It's just, it will be sometime soon. So what we're going to do next is we're going to talk about next gen and unmanned aircraft systems, and that'll be it.